All right, so let's go over this. So this was an old exam problem, exam 2. And will give us some more practice with factor groups. I want to focus today mostly on chapters 9 and 10, factor groups and homomorphisms, and something hopefully especially called the First Isomorphism Theorem. We'll continue talking about those things next Monday, as well as review other things for the exam on Wednesday. I will share these exams with you. Maybe I'll just email them quick to you after class, but then I'll ultimately also put them on Moodle. So the problem starts by saying, consider this U group. Well, when we have a subscript there, it's really a subgroup of U30. It says here. It's all the elements in U30, where when you mod by 5, you get 1. Okay, you've read about this. It turns out this is a subgroup of U30. And if you figure out the elements, first of all, here are the elements in U30. You want all the numbers between 1 and 30, 1 and 29 that are relatively prime to 2, 3, and 5. So you don't want any even numbers. You don't want any multiples of 3 or any multiples of 5. And of those, when you mod by 5, there's only 2 of them that give you 1 for the remainder, 1 and 11. And yes, that is a normal subgroup of U30, because certainly in any abelian group, all subgroups are normal. Say that again. Certainly in any abelian group, all subgroups are normal. Certainly A equals Ha, right? The left coset containing A will equal the right coset containing A if G is an abelian group, because A little h equals H little h times A for every little a and little h in the group. So certainly in abelian groups, all subgroups are normal. So you can go ahead and write the triangle instead of just a less than symbol to emphasize a normal subgroup. Somebody had a question about this on the assignment I think I handed back to you. Something I think I did mention in the lectures, but I forgot to, or I just haven't emphasized here in class. Different U groups where you have different numbers in here, 30 as opposed to say 90 or 200 or 1,000 or 3,000, whatever. When you've got different numbers in the U groups, they're never subgroups of each other. They could be subsets. One U group could be a subset of another U group, but they're never subgroups because the operation's not the same. Because you're always modding by whatever number's in there. Multiplication mod that number. And if you've got a different U group, it can't possibly be a subgroup because it's a different operation. You're modding by a different number. Same kind of thing with the Z groups. You know, Z3 is a subset of Z6. But Z3 is not a subgroup of Z6 because the operation is different. Addition mod 3 versus addition mod 6. Subgroups have to have the same operation. Okay, just a little side note that I haven't emphasized in here, but I think I did mention in the lectures. All right, so then the question is, what is the order of this left coset in the factor group? What factor group? This one. U30 is the entire group, this thing. We're modding by, sometimes I do say modding by, to form the factor group, this subgroup, this normal subgroup. The elements of this factor group groups are also known as quotient groups, but we'll say factor group because that is what our book does. The elements are left cosets. Why left cosets? Why not right cosets? Well, we could have chosen right cosets, but that just wasn't the choice that the first person who thought about this made. So we're stuck with left cosets. But wait a minute, with normal subgroups, left cosets equal right cosets. So actually, they're equivalent to each other. The elements of the factor group are all the distinct left cosets. The operation of the factor group, remember, is aH times BH is aBH. The left coset containing A times the left coset containing B, by definition, is the left coset containing A times B. So you've got to prove that that makes sense. It's well defined by showing if you picked a different representative for these cosets, an A prime and a B prime, to get A prime times B prime times H, that it would be the same answer. That it would be AB and A prime B. A prime B prime would be this different representatives still of the same coset. How do you figure out the order? Well, you just got to keep raising it to higher powers and see when you get back to the identity. 17 squared is 289. Technically, I really probably shouldn't write this thing here because 289 is not an element of U30, but you know what I mean, right? Simplify it though by modding by 30. 289 divided by 30 would have a remainder of 19 because 30 goes evenly into 270. And 19 is not in the subgroup. So this is not the identity. If I had gotten 11 there instead of a 19, I would have been done. And the order of this would have been 2. Say that again. If I had gotten, well, a 1 or an 11 here instead of a 19, 1 and 11 are in the subgroup. Therefore, this would have been the identity coset of the factor group. And I would have been done, and I would have said the order of this is 2. But it's not 1 or 11, it's a 19, so I need to keep going. If I raise it to the third power, that's equivalent to taking it times its square. 17 times 19 is 323. Again, technically, I probably shouldn't really write this because it's not really, 323 is not in U30. But again, you know what I mean. It's not a big deal if you do write it. I know what you mean. Ultimately, we do need to mod by 30, though, to get an element that is in U30. Yeah, 323 divided by 30 has a remainder of 23 because 30 goes evenly into 300. So it's going to be a 23 here. Yeah, and 23 is not in there. The order can't be 3. Try fourth power. Here I did this one squared. I squared the square. So you see a 19 squared there, which is 361. Again, technically I shouldn't write this, but I did, and you can as well. But 361 divided by 30 has a remainder of 1 because 30 goes evenly into 360. So I get a 1 there, which you don't have to write. That is the identity coset. You're back to the identity element of the factor group. Therefore, the order of this thing is 4. Last question is this thing cyclic? And the answer is yes, it is. I forgot if the question asked for the order of it. No, it actually didn't ask for the order of the group, but it's worth thinking about as far as explaining why it's cyclic. The order of the factor group, this entire expression is the order of the factor group by Lagrange's theorem. This is really Lagrange's theorem. Is the ratio of the order of the entire group divided by the order of the normal subgroup. Why? Well, by definition, the order of the factor group is the same as the index of the subgroup in the entire group with this notation. Why? Can you tell me why? Why are these the same by definition? I claim it is by definition. What do I mean there? A couple definitions. The definition of the symbol and the definition of the factor group. Can you elaborate? Why are these the same? Yeah, the number of left cosets. By definition, the index of a subgroup in a bigger group is the number of left cosets. which you can always define whether the subgroup is normal or not. Here the subgroup is normal, so we can also form the factor group, but the elements of the factor group are the left cosets. So you're going to have the same number of elements of this group as what we define the index to be. And by Lagrange's theorem, again, that's the order of the entire group divided by the order of the subgroup. And the order of the entire group, looking back up here, is 8. And the order of the subgroup is 2. There's 2 elements in the subgroup. 8 divided by 2 is 4. This factor group is a 4-element group. And hey, it's got an element of order 4, therefore it's got to be cyclic. And that's got to be a generator. Question?
Does that work for every factor group where you can divide the
Finite ones, at least.
Okay.
Yep. That doesn't quite work for when you're dealing with infinite groups. The factor group can be finite even if the group itself is infinite. A prominent example is take Z, the infinite cyclic group, our standard infinite cyclic group, and mod by a subgroup, say, consisting of all multiples of 3Z. That's the same as the cyclic subgroup generated by 3 is all multiples of 3. Both of those things are infinite sets. The order of Z is infinite. The order of 3Z is infinite. The factor group is finite, though. It's got 3 elements. The factor group, as you've seen examples in the book, written with additive notation, has these 3 elements: 0 plus 3Z, 1 plus 3Z, and 2 plus 3Z. Because, for example, 3 plus 3Z would be the same as 0 plus 3Z, but the 3 would get absorbed, so to speak, by that thing. It would sort of get absorbed into it, is the way you imagine it. Why? Because it's an element of it. Just like aH equals H if and only if A is actually in H. This is the same idea, except with additive notation instead of multiplicative notation. 3 is in 3Z, so it gets absorbed into it. If I had a 6 plus 3Z, the 6 would get absorbed into it. 6 plus 3Z would also equal 3Z. Weird stuff, huh? But that's what these definitions imply. Just different note. It's this idea right here. It's just different notation. Additive notation instead of multiplicative. So coming back to your question, this is finite, but I cannot write it as a ratio of infinity over infinity. At least not thought about in the usual way. You can't divide by infinity. Maybe there's a non-usual way to do it. I don't know. I won't go into it. But yeah, if your groups are finite, if G is finite, and H is a normal subgroup of G, then the order of the factor group is the ratio of the order of G to the order of H, which you might say is another good reason for this kind of notation for factor groups, to make it look like a division. It is kind of analogous to division in some ways, but not completely. Can I clarify anything else? Let me mention one more thing about this example. U30, according to theorems from chapter 8, is isomorphic to, well, 30 again is 2 times 3 times 5. This would be isomorphic to U2 external direct product with U3 external direct product with U5, right? Because 2, 3, and 5 are all relatively prime. And based on other facts in chapter 8, that's isomorphic to, well, U2 is just a 1-element group. The book writes it as a 0, that it's isomorphic to the trivial group with a 0, or it could have been with an E, it could have been with even a 1 to emphasize that the one element of this is the number 1. 1 would be a trivial group under multiplication. 0 is a trivial group under addition. It's a trivial group either way. U3 is isomorphic to Z2 and U5 is isomorphic to Z4. And in this kind of thing, you can sort of say, well, this doesn't really do anything for you. This whole thing is actually isomorphic to Z2 external direct product with Z4. Because this doesn't really add anything, so to speak. Just being a one element group, it turns out you can sort of get rid of it. I'm not going to explain fully why here. And this is a 2 element group, subgroup, it's isomorphic to Z2. So the factor group should be isomorphic to the factor group of this by this. Well, at least if you thought of this thing in the right way, if you think of it as being Z2 external direct product with a trivial group. Oh, yeah, and I do want that to be a 0 there because I wanted to think of this as a subgroup of this. In other words, what I'm trying to get at is if you form the factor group Z2 external direct product Z4 by Z2 external direct product with 0, that should be isomorphic to this thing, which we said is cyclic, and so it's isomorphic to Z4, cyclic lower 4. Does that mean we can in this kind of expression, we can kind of cancel the Z2s and get this, and then maybe say, well, that's a one element group, maybe this is isomorphic to Z4. Is that justified? Yeah, but I'm not going to explain why fully here. So there's another good reason for the pseudo fraction notation is you can sometimes do some cancellation. Not going to fully explain it. Okay. Let's think about the well-defined issue again. So the book proves the well-defined product and factor groups using properties of cosets. Let's look at this again. So what we're doing is we're assuming aH equals A prime H and BH equals B prime H. More officially, the left coset of H and G containing A equals the left coset of H and G containing A prime, and same kind of thing with B and B prime. This means A prime equals A times H1 and B prime equals B times H2 for some H1 and H2 and H. Is that obvious? Well, it is to somebody who's worked with factor groups enough, maybe less obvious to those who have not. Why can you claim this? Well, A prime certainly is in A prime H. It's certainly in the left coset of H and G containing A prime. It equals A prime times E, and E is an H. Therefore, since these are equal, we're assuming these are equal, it's also in there. And therefore, it is A times something in H. Call it H1. That kind of thinking, you need to get to the point before Wednesday where that kind of thinking is pretty automatic for you. You've worked with this kind of stuff enough, done enough practice problems, thought enough about it that that becomes an almost automatic thing. You hardly have to think about it. Same kind of thing here. B prime is in B prime H because it equals B prime times E. E is in H. H is a subgroup. Therefore, it's in there because we're assuming these are equal. Therefore, it is B times something in H. Not necessarily B times E, B times something else in H, call it H2. So then, ultimately, the goal is to show A prime B prime H equals ABH. What the author is doing here is using properties of subgroups and also the definition of coset multiplication, I think. Let's see here. A prime B prime H, why does that equal this? Because A prime equals A times H1 and B prime equals B times H2. That's just substitution. What's the justification for that step? Yeah, H2 is an H. It got absorbed. It gets sucked into H. You can even making like a sucking sound. Don't do that during the test. In your mind, you can imagine H2 getting like sucked into capital H. That's the way algebraists imagine it, actually. Because it is an H. Technically, you might say you're using the associative property too there with, you're sort of thinking of it as AH1, BH2, H. You're sort of thinking of it as being the same as AH1B, H2H with the parentheses like that, say. And then this is H. H2 gets sucked into H. And that ultimately is the same as AH1BH. So, I mean, there's some associativity going on, but once we've proved the associative property holds, we hardly ever mention associativity. We just use it whenever necessary. Going from here to here, what's the reason? H is normal, right? BH equals HB. Then, hey, another sucking in. H1 gets sucked into capital H. And then you got aHb, focus on the AH, or focus on the HB again. Once again, H is normal, that's the same as BH. So the book is doing this in kind of a, you might say, a fancy way with coset properties. Is it possible to do this in a less fancy way? Yes. If your goal is to show A prime B prime H equals ABH, what I'm saying by a less fancy way is not using properties of cosets, just the definitions of these sets, these cosets, not the properties. For example, these are two sets. We'd want to show that each one is a subset of the other, like this is true, and this is true. This would be another way to try to show it. That the group operation here in the factor group is well defined. Well, these are real symmetric kinds of things. I bet if we show one of them, we could just say the other one follows by symmetry. Yeah, it does, because these symbols are arbitrary anyway. Does that make sense? Let's show this one. And if we do it for that one, we've essentially done it for the other, because again, the symbols are really arbitrary. A is an arbitrary element of H, so is A prime, or excuse me, of G. Yeah, these are equivalent kinds of things. So how do you do this? You could start by saying let, what should I call it? Maybe X be in ABH. What does that mean? That means there exists, call it an H1 maybe, in capital H, such that X equals ABH1. But since H is normal in G, H normal in G implies there exists, call it an H2 in capital H, such that, say, BH1 equals H2B. If the group were abelian, H1 and H2 would be the same. But in general, you can't assume it's abelian. But it is normal. So yeah, I mean, I'm essentially using the fact that BH equals HB here in saying this. So X equals aH2B. What's my goal here? My goal is to show X is in here. I do need to relate these things to A prime and B prime. I didn't think about that yet. Let's see. I am assuming, okay, I got to use the assumption that AH equals A prime H, BH equals B prime H. That those assumptions have to be used, or at least one of them does. Let's go ahead and use maybe this one here first. Focus on AH2. The fact that I'm assuming AH equals A prime H means that AH2 equals A prime H3 for some H3 in H based on this. That's the way to get the A prime in there. Maybe I should do this something similar for B and B prime. I'm not claiming this is the best way to do this problem. Use this fact. Replace B with, okay, it's not next to an H. I can't do that yet, can I? It doesn't have an H on its right. Don't do it yet. This is scratch work, really. Think of it this way now, and replace H3B with BH4 for some H4 in H. And now I can use the other one. I can say BH4 equals B prime H5 for some H5. And in going into this, I had no idea that I would have 5 different elements in H to think about there. And this is definitely an element of A prime, B prime, H. I think the book's method is definitely more elegant. Perhaps there's a way I could be more efficient here. Maybe I'm not being as efficient as I could be. You could do this at the element level, and what I did here essentially proves this subset inclusion. The other one would be analogous, and we could say that this is true.
Is that goal the same for always proving that opportunity all the time?
In factor groups. That does bring up another issue, another place where well-defined comes up in the next chapter, which I think would be good here to start now. 25 minutes left here. Chapter 10 is about group homomorphisms, not isomorphisms. What's a group homomorphism? A group homomorphism is a function from a group to another group that is operation preserving, but not necessarily one-to-one and not necessarily onto. Phi going from G1 to G2 is a group homomorphism if, this is a definition, it's operation preserving. Maybe I shouldn't have used subscripts, but oh well. Ignore that scribble. That's the definition. Nothing about phi being onto, nothing about phi being 1-to-1. Of course, phi could be 1-to-1 and onto, and if it is, then the group homomorphism would also be a group isomorphism. So isomorphisms are homomorphisms, but homomorphisms are only isomorphisms if they're also 1-to-1 and onto. I'm going to go ahead without talking about this concept and its properties and jump right to the chase, jump right to the punchline. The main consequence of this definition, one of the main consequences, is something called the First Isomorphism Theorem. And if there's a first isomorphism theorem, there must be a second one. Yes, there is, and there's even a third. We're mostly going to focus on the first, though. And the reason I'm bringing this up, first of all, is because it's really important. Secondly, because it will, as Michelle asked, and as I would actually want it to do anyway, it will offer us another chance to think about the issue of when a function is well-defined or not. And it'll offer us another chance to think about factor groups and another chance to think about cosets. These all come into play here. First isomorphism theorem. Let me not use subscripts here. Suppose I think the book uses G and G bar. G and G bar are groups. And phi going from G to G bar is a homomorphism. Our book might also assume that's onto. I'm forgetting. No, it doesn't. Okay, that's fine. I was not going to assume it's onto. Then, well, I'm going to say a little less than the book does here. The book says a little bit more than what I'm going to say here. Then the factor group G modded by, if you like, what's called the kernel of phi. You've heard of kernels before, haven't you? Null spaces, linear algebra. I haven't mentioned it here yet. We'll talk about it after I write it down. This factor group is isomorphic to the factor of the group that is the image of G under phi. Image of G under phi. It's the set of all outputs of phi as little g ranges over capital G. And it's a subgroup of G bar. What is the kernel of phi? Again, you've thought about this concept in linear algebra, the kernel of a linear transformation, also called the null space of its matrix. What's a null space of a matrix? It's the set of all vectors x such that a times x is the zero vector. Kernel of a linear transformation T between two vector spaces, set of all vectors x that get mapped to the zero vector. Vector spaces are groups under addition. I mentioned that before, ignoring scalar multiplication. What's the zero? I gave it away. What's the identity element of a vector space? The zero vector. The operation's addition. Kernel generalizes that concept to a group homomorphism. Kernel of phi. It's the set of everything in G, capital G, that gets mapped to the identity element of G bar, I'll call it E bar. Identity element of G bar. If we were talking vector spaces here, if G and G bar were vector spaces where the operation is addition, it'd be the set of everything in G that gets mapped to the zero vector. Kernel of a linear transformation. Linear transformations are group homomorphisms under addition. They are operation preserving. If you look back in your linear algebra book, but the definition of a linear transformation, you'll see it says T of U plus V equals T of U plus T of V. That's operation preserving under addition. I'd like to talk about the idea of the proof of this. Here's this big important theorem. Haven't talked about any applications of it yet. I'd like to talk about the proof right away. I'm not going to do a full polished proof, just talk about the idea of it. You should be able to understand this proof for the exam and maybe do part of it on the exam. It's an important enough proof to work through, and it's doable. You can do it once you see the idea. How do you prove an isomorphism like this? You'd have to come up with an isomorphism. An isomorphism from this factor group to that image. And by the way, if phi is onto, note, if phi does happen to be onto, but not necessarily one-to-one, then this says that G by the kernel of phi is actually isomorphic to G bar, the entire group, because if phi is onto, then its image is the entire group G bar. And so it's nicest to apply this when phi is onto, you might say. Or you might as well just consider the image as being what G bar is. Maybe that is another way to think about it. Well, how would you prove this? It's definitely not obvious how to prove it. I'm going to draw a diagram that is, I think, a pretty helpful diagram to think about. It's called a commutative diagram. And you'll find diagrams like this actually in your linear algebra book. Not exactly the same thing, but kind of like it. Another way to think of, besides this, to write functions. Oh, I started it wrong. Scratch that. Another way besides this to picture functions is to put the function name above the arrow. That also is shorthand notation for phi being a function from G to G bar, not necessarily onto. In other words, the domain is G and the codomain is G bar, but the image does not necessarily equal the codomain. Let me put the factor group G mod the kernel of phi down here. I would like to come up with an isomorphism, actually. Phi is a homomorphism. I would like to construct an isomorphism from this thing to this thing. Well, let's go ahead, just for simplicity, assume phi is onto. Let's go ahead and assume that. Without less generality, you actually can assume it. Again, because you could just take G bar to be whatever the image of phi is. in some possibly bigger group to which phi is not necessarily onto. In other words, you can always shrink your codomain if you want to make your function onto. It's all just a matter of perspective and how you're thinking about it. That's all it is. Think about a blob picture. If that's G and this is G bar, the image might be smaller than G bar. But if it is, then you could shrink G bar to be just this, be the actual image. So that you can always assume this without loss of generality, you might say. This is a big question mark. What should that this function be? What is the isomorphism? Maybe I should call it something. Call it, how about, I don't know, phi bar. Is that what the book does? No, the book calls it psi. Okay, let's scratch that and call it, let's call it psi to be consistent with the book. But psi, if you think about it intuitively, must be related to phi. You must have to use phi to construct psi, because what else would you do? That would be the natural thing to do. We've got nothing else to do. That's the thing, the only thing we're given. We must have to use it somehow. Phi is not necessarily one-to-one. Psi does need to be one-to-one to be an isomorphism. Somehow it's like the kernel is perhaps what's preventing phi from being one-to-one or something. Maybe. And by doing the factor group, maybe that somehow allows us to take phi and make a one-to-one mapping. Still probably not very clear. Other than to say we've got to define psi applied to an arbitrary coset of the kernel, because the elements of the factor group are cosets, left cosets. I got to come up with a formula for something like this. What should this equal? It's got to be an element of G bar, which again, I'm assuming is the image of phi, of G under phi. What's the only natural thing to guess? Do you have a guess? Has your intuition been trained enough by now that you've got to guess? How could I take these symbols, well, the G and the phi especially, and make an element of G bar in a natural way? That involves phi and G. And I almost gave it away just by saying that. What's a way I can take the symbols, the G and the phi, and from those symbols where I'm assuming this kind of thing is going on here, and G is an element of capital G, and make an element of G bar. Phi of G. That's like the only thing to try. But hey, if you try it, you do need to show it's well defined. Why? Because what if we had a different representative for this coset? Instead of G, a G prime, say. Is phi of G equal to phi of G prime? Does this formula make sense? That is an issue that needs to be thought about and proved. That does make sense. This diagram is not complete. There's another mapping to add to this diagram. From G to G mod the kernel of phi, the factor group of G by the kernel of phi, that will help this diagram commute in the sense that it won't matter what direction you go from G to G bar here, you get the same thing. If you apply phi, or if you go down to the factor group and then over here, you're going to end up with the same element. What am I talking about here? This homomorphism, this homomorphism from G to this factor group, and it will be a homomorphism, is often called pi. It's not the number pi. It's just the letter pi. It's standing for the homomorphism here. It's just a Greek letter that's standing for a certain function. I don't think the book calls it that, but yeah, they actually call it gamma. The book calls it gamma. But I always learned it as a pi, a lowercase gamma here. Pi is called the natural homomorphism from G to this factor group, and it's defined by mapping an arbitrary element of capital G to the left coset containing capital, mapping an arbitrary element of capital G, call it little g, to the left coset of the kernel in capital G containing little g. Pi of G equals G kernel phi. And that makes this thing become psi of pi of G. And that, the equality here can also be written with composition notation. Psi composed pi equals phi. Or since our book does not bother putting circles for composition, psi pi equals phi. I always learned this as a pi because pi starts, if you write it out in English, is spelled pi, and pi starts with a p. And this is also called a projection mapping sometimes. And the word projection starts with p. So that's why other people use a pi, but our book author called it a gamma. Anyway, we've got to show this is well defined. Let's end class today by doing some scratch work to see if we can figure that out. Is this formula well defined? Suppose G cur phi equals G prime cur phi. The left coset of the kernel in G containing little g equals the left coset of the kernel in capital G containing G prime. Does phi of G equal phi of G prime? If it does, that means it's well defined. Get the same output. If it doesn't, that means it's not well defined. Well, obviously the answer must be yes, it is. Otherwise, we wouldn't be doing this. How would you show that? Here's one way. Remember this property of cosets? AH equaling BH is equivalent to, for example, A inverse B being an H, which is also equivalent to B inverse A being an H. Remember that? It's property of cosets. Thought about intuitively, you could take that equation and multiply both sides on the left by A inverse. And then use the associative law and that's the identity This is saying H equals A inverse B H. And that equality would mean A inverse B is an H. Careful, the inverse does have to be the one on the left. This is not equivalent to, I'll put a big not through it, A B inverse being an H, for example. Not equivalent to that, unless the group happen to be abelian. So the fact that this is, I'm supposing this is true, that means I can say, for example, G inverse G prime is in the kernel. Well, what does it mean to be in the kernel? That implies phi of G inverse G prime equals E bar. E bar is the identity in G bar. But hey, phi is a homomorphism. It's operation preserving. This is the same as phi of G inverse, phi of G prime, and then you can also bring the inverse out like this, phi of G inverse, phi of G prime equals E bar. And now just multiply both sides on the left by phi of G. And you get phi of G prime equals phi of G. I just left multiplied by phi of G, and the inverse is canceled. And that's what we wanted to show. Yeah, these are equal. And that shows that the psi function is well defined. That's probably actually a little easier than the well-defined issue with the factor groups. Okay, we haven't had time to talk about applications of this stuff. I know that's probably on your mind prominently. I did mention some of them briefly last time, like the GZ theorem and Cauchy's theorem. There's also some applications to internal direct products and classifications of groups that are facts you should know for the exam. So make sure you continue reviewing those things from chapters 9 and also now in 10. All right, have a good weekend.